Hello everyone, my name is Greg, and today I prepare for you 6 questions from Principles of Flight exam seen in the last 30 days across all authorities. Topics for today are stalls and UPRT. Let's go to question number 1. A pilot performs the recommended actions to recover from a fully developed spin. Once the rotation has stopped and control has been regained, the pilot applies aft elevator to return to level flight. Excessive aft elevator pressure may result in. And the answers are flattening of the spin attitude and delayed recovery, a secondary spin in the opposite direction, flattening of the spin attitude and rapid recovery, and the last one, a secondary stall or a load factor accidents. Right, so for this question, let's talk first about the load factor. As you probably know, the load factor is a ratio between lift and weight. In level unaccelerated flights, lift equals weight, therefore load factor is 1. For maneuvers like turns or pulling out, lift not only has to balance the weight, but also overcome aircraft inertia to change the direction of the movement. If we pull abruptly enough, we will generate so much lift and so strong low pressure area that relative flow won't have enough energy to overcome the adverse pressure gradient and will separate from the wing. This is called an accelerated stall, and it may happen in much higher speeds than VS1G. Now, at higher speeds, the same maneuver creates a higher load factor, and each aircraft has load factor limits set in AFM. There's a very important speed that we have to keep in mind at this point, the design maneuver speed, VA. It is the highest speed at which a sudden full-up elevator deflection can be made without exceeding the limit load factor. So what does it mean in practice? If we fly below VA, the abrupt full-up deflection of the elevator will cause an accelerated stall. If we do the same above VA, the structure may distort or fail. More details you may find in limitations section of Principles of Flight, where you will learn about the maneuver envelope, which covers this topic. So, checking the possible answers, we can see that answer number 4 will be correct, a secondary stall or a load factor accidents. Alright, question number 2. An aeroplane is executing a misapproach after entering microburst on the approach. The airplane may be very close to stall due to increasing airspeed, increased tailwind, initial reduction in the rate of descent, or energy gain. Microburst is a phenomenon usually associated with cumulonimbus clouds and is an intense downburst of the air. When it hits the ground, it spreads in all directions with a diameter of 4 km or less, causing rapid changes in wind, speed, and direction. Now, when an aircraft is entering a microburst, it encounters a sudden energy gain and an increase in headwind, resulting in initial increase in airspeed and reduction of the rate of descent. In the middle of the microburst, on the other hand, an aircraft encounters a severe downdraft. Headwind decreases or might change already to tailwind, and we have to expect a massive sink. The last stage of flying for the microburst is associated with a sudden increase in tailwind. This tailwind may deplete the airspeed before engines will have time to react. This can bring us extremely close to the stall if we want to perform a windshield escape maneuver in which one of the items is a full toga. So looking at the answers, the correct answer will be answer number 2, increased tailwind. And it's a correct one. Question number 3. If a light airplane has accumulated ice on the horizontal stabilizer while flying in icy conditions, and the pilot takes no action to address this, then during the landing flare, the aircraft may suffer a tail stall end. And we have, like always, 4 options. So, icing is one of the most important threats that has to be addressed on everyday basis. Any buildup of ice on the wing or elevator surfaces significantly reduce lift and increase drag to weight. Now, ice changes the profile and increases roughness of the surface, causing early flow separation and effectively reduces stalling angle of attack and CL max. Now, as we know, the horizontal stabilizer produces a downwards force to balance the center of pressure and center of gravity arm. With stalls, the aircraft nose would pitch down and nose wheel can contact the runway first. Moreover, if the horizontal stabilizer already has stalled, the elevator would not have any effectiveness or very little, because elevator movement changes the CL on the horizontal stabilizer, increasing or decreasing downforce. If we pull up, it would increase the CL, only deepen the stall. Now, going through the answers one by one, the first one is incorrect because it would be a nose down pitching moment, so no nose up pitching moment. Answer number 2, here it says that the pitching moment would be easily controllable with elevator, and like I said before, elevator would have very small, if any, authority. So this one is also false. Answer number 3. Well, since we are flaring, we are already over the runway. Therefore, I would say there is no chance to undershoot it. So I wouldn't choose this one. And the last one, answer number 4, is very likely the outcome and of the situation, and this will be a correct one. So the nose down, the tail stir will cause a nose down pitching, causing the nose wheel to contact the runway first. And that was correct. Question number 4. What is correct about a fully developed spin? Speed is slow and constant, spinning rate increases, speed increases, and spinning rate increases. Speed is slow and constant, and spinning rate is constant. Speed increases and spinning rate is constant. Okay, the very first and important thing is that the prerequisite for any spin is the aircraft being in the stalled condition. This is one of the differences between spiral dive and spin. In spiral dive, an aircraft is actually still flying and the speed is increasing with a high rate. In a spin, on the other hand, we are not flying. We are stalled and just falling down like a rock. Now, the characteristics of the fully developed spin is that yaw, slip, and roll are stable at low stable speed. And this condition should stay stable even without any pilot input. Well, at least in theory. Now, this stability is a key difference between an incipient spin and fully developed spin. In incipient spin, an aircraft begins the auto-rotation, but the aircraft motions are not stabilized yet, and at that moment, standard stall recovery should be sufficient to recover from this situation. Now, the fully developed spin starts after the first 360 turn, where yaw, slip, and roll become stable. So as we see, a fully developed spin would have low speed and constant spinning rate. So answer number 3 is correct. Now, question number 5. Which statement is correct? Stall speeds are determined with the CG at the aft limit. And statement number 2, minimum control speeds are determined with the CG at the aft limit. Remember that whenever we talk about limitations of any kind, they are determined for the most unfavorable conditions. Therefore, the first statement is incorrect because the most unfavorable CG position resulting in high stall speed is the forward CG position, not aft one. Forward CG position creates a greater R between the center of gravity and the center of pressure. To overcome nose-down pitching moment created by this arm, the horizontal stabilizer must provide bigger downforce. As a result, an increase in lift is needed to balance these down-acting forces. Subsequently, as we know, greater lift means higher stall speed. The second statement is dealing with CG in determining minimum control speed, VMC. VMC is a general term for minimum control speed with critical engine inoperative. But in reality, we have 3 different minimum control speeds. VMCG, minimum control speed on the ground, where the directional control can be maintained solely by the rudder inputs. And as a side note, please remember that on the ground, the arm that influences the rudder effectiveness is built between main landing gear and rudder, and not between CG and rudder. Now, for this question, we are more interested in VMCA and VMCL. VMCA is a minimum control speed in the air, also per CS definition, minimum control speed takeoff climb, and VMCL is a minimum control speed during approach and landing. These two are minimum calibrated airspeeds at which an aircraft is still controllable with full power on the live engine with maximum of 5 degrees bank angle, maintaining directional control with a rudder. Now, what happens if we have CG in the aft limit? The arm between CG and the rudder becomes shorter, requiring a greater force from the fin to maintain directional control and reducing its effectiveness. To regain full directional control in this case, we need higher CAS. So as we can see, aft CG position regarding VMC is unfavorable position, therefore the second statement is correct. So let's select answer number 3. First it is incorrect, second statement correct. And this is the correct answer. Alright, the last 6th question. An aircraft comes out of a large maintenance overhaul, which include both wings being disassembled and reassembled. But they were accidentally reassembled with slightly different angles of incidence. During the post-maintenance check flight, the pilot must fly close to the stall speed. Which of the following may happen in this situation? Alright, let's first dig into what angle of incidence is. Normally, aircraft are designed in a way that wings are mounted with a slight positive angle. The definition of an angle of incidence is an angle between the chord line of the wing and the longitudinal axis. Now, most designs utilize a twist, reducing the angle of incidence from the root towards the wingtip, something that we call a washout. The purpose of it is to reduce the tendency for wingtip to stall first in certain designs, like for example in a swept wing or high taper design. Now, if we consider a case from the question, since wings had been reassembled with slightly different angle of incidence, it's easy to imagine that the wing that had been mounted with a greater angle of incidence during a flight would have a greater angle of attack. During an approach to stall maneuver, this wing will reach its critical angle of attack and stall sooner than the wing with smaller angle of incidence, and that will result in a wing drop. And exactly this situation is described in answer number 3. The wing that was reassembled with higher angle of incidence stops first, causing a wing drop. And that was the correct answer. Alright, that was all for today. I hope you enjoyed, and see you next time.